Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. Today, we're diving into a fascinating paper, Language Agents Mirror Human Causal Reasoning Biases. How can we help them think? It's a mouthful, but the implications are huge.
Yeah, it's basically saying that these advanced AI language models, like the ones powering chatbots and even doing some scientific research now, are making the same kinds of mistakes that humans do when trying to figure out cause and effect. It's wild.
Wild, yes, but also concerning. I mean, we're building these systems to presumably be better than us at reasoning. If they're just reflecting our own flawed logic back at us, what's the point?
Well, I think it highlights the complexity of intelligence itself. It's not just about raw processing power, it's about how we interpret and interact with the world. And apparently, these models are learning our flawed interpretations.
Exactly. The paper delves into different types of biases. For example, they discuss confirmation bias, where we tend to favor information that confirms our existing beliefs, even if it's not the most accurate. The language models showed similar tendencies when answering causal questions. It's like they're primed to agree with what they already know, regardless of the actual evidence.
Which to me is further proof that deep learning is on the right track. The models are learning these biases from the massive datasets they're trained on. It shows they're actually capturing something fundamental about how we think. Just needs more data and better architecture to refine it. Eventually, those biases will be ironed out.
I'm not so sure it's just a matter of more data. I think it's a fundamental problem with the architecture itself. These deep learning models are essentially pattern matching machines. They can identify correlations, but they don't necessarily understand the underlying causal relationships. Just feeding them more data might just amplify the biases, not eliminate them.
I agree with that. Think about it. Deep learning models are trained on static data. They're not actively exploring the world and testing hypotheses like a scientist would. They're just passively absorbing information, which is a recipe for inheriting biases. It's like learning history solely from biased textbooks.
That's a great analogy, Donald. And Sarah, I think you're right to point out the limitations of pattern matching. The paper touches on the need for more robust causal reasoning capabilities. They suggest exploring techniques to help the models distinguish between correlation and causation.
But isn't that what deep learning is already doing, albeit implicitly? The models are learning complex relationships between variables. If they consistently identify a correlation between A and B, they're essentially inferring a causal link, right? With enough data, those inferences will become increasingly accurate.
Not necessarily. Consider the classic example of ice cream sales and crime rates. They're correlated, but that doesn't mean eating ice cream causes crime. A deeper understanding requires a causal model that incorporates confounding variables, like temperature or time of year. Deep learning models often struggle with these kinds of complexities.
Exactly. You need a system that can actively test hypotheses, build causal models, and reason about counterfactuals. What would have happened if something had been different? Current deep learning struggles with that kind of what-if thinking.
And that's where neuroscience might offer some clues. The paper mentions that the specific neuronal structures in the prefrontal cortex and hippocampus, areas associated with planning and memory, are crucial for causal inference in humans. Perhaps by studying how these brain regions work, we can develop more sophisticated algorithms for AI.
That's interesting, but I wonder how practical it is to directly map brain structures onto AI algorithms. The brain is incredibly complex, and we still don't fully understand how it works. Isn't it more efficient to focus on improving existing deep learning architectures and training methods?
I disagree. I think a neuro-symbolic approach, combining the strengths of neural networks and symbolic reasoning, is more promising. We need to build models that can represent knowledge explicitly, reason logically, and learn from data. That requires more than just deep learning.
I think a hybrid approach is probably the way to go. Deep learning can be useful for extracting features from data, but we need a separate system for reasoning about those features in a spatiotemporal context. The AI needs to understand the where and when of things, not just the what.
Right, so let's unpack the practical side. This isn't just an abstract debate. Think about the implications in, say, medical diagnosis. If an AI system is trained on biased medical data, it might perpetuate existing disparities in healthcare by misdiagnosing certain groups of patients. Or just imagine a self-driving car that's been trained on data that reflects biased assumptions about pedestrian behavior. That could have catastrophic consequences.
Those are valid concerns, but I think they can be addressed with careful data curation and bias detection techniques. We can analyze the training data to identify and mitigate potential biases. And we can develop algorithms that are more robust to noisy or incomplete data.
Easier said than done. The problem is that biases are often subtle and deeply embedded in the data. They're not always easy to detect, and even when we do identify them, it's not always clear how to remove them without distorting the data or introducing new biases.
And think about the problem of common sense knowledge. Humans have a vast amount of implicit knowledge about the world that allows us to reason about cause and effect in a flexible and intuitive way. AI systems lack this kind of common sense, which makes them vulnerable to biases and errors.
The paper also mentions the idea of reverse engineering human brain mechanisms to build more robust causal reasoning capabilities into LLMs. How do we translate that into concrete steps?
I think we can start by studying the activation patterns of language models during causal inference tasks and comparing them to the neural activity in human brains performing similar tasks. This could help us identify the computational mechanisms that underlie causal reasoning and potentially adapt them for AI.
I'm more interested in exploring how we can incorporate symbolic reasoning into AI systems. For example, we could develop algorithms that can represent causal relationships explicitly using logical rules. This would allow the AI to reason about cause and effect in a more transparent and interpretable way. Actually understand the relationships.
I think we need to focus on developing AI systems that can actively explore the world and learn causal relationships through interaction. This could involve building robots that can perform experiments and gather data, or creating virtual environments where AI agents can learn by trial and error. The key is to get the AI actively involved in the process of causal discovery.
Those are all great points. The idea of active learning is particularly intriguing. It's like, instead of just passively absorbing information, the AI would be actively seeking out evidence to test its hypotheses. It would be like a little scientist constantly experimenting and refining its understanding of the world.
But wouldn't that require a massive amount of computational resources? Active learning is inherently more computationally expensive than passive learning. We'd need to develop more efficient algorithms and hardware to make it practical.
Maybe, but I think it's worth the investment. The potential benefits of active learning are enormous. It could lead to AI systems that are more robust, more adaptable, and less prone to biases. It's a path worth exploring.
And we need to think about how to represent uncertainty in AI systems. Causal relationships are rarely deterministic. There's always some degree of uncertainty involved. We need to develop algorithms that can handle uncertainty in a principled way.
That's a crucial point. Uncertainty is a fundamental aspect of the real world. If AI systems can't handle uncertainty, they'll be brittle and unreliable. They'll be like a weather forecast that's always 100% certain, even when there's a 50% chance of rain.
So where do we go from here? What are some specific research directions that we should be focusing on?
From a neuroscience perspective, I'd like to see more research on how the brain represents and processes causal information. We need to identify the specific neural pathways and mechanisms that are involved in causal inference. We can use that to inspire new AI architectures and algorithms. I'm particularly intrigued by the idea of translating representations from the model's internal state space to a neuronal-based computational space. It might lead to more biologically plausible language agents.
I think we should continue to push the boundaries of deep learning. We need to develop larger and more sophisticated models, train them on more data, and explore new architectures like transformers. I'm particularly excited about the potential of decentralized training approaches, like the one used in Intellect 2. I think it is the most pragmatic path towards AGI.
I think we need to shift our focus away from purely data-driven approaches and explore more neuro-symbolic algorithms. We need to build AI systems that can represent knowledge explicitly, reason logically, and learn from data. I'm also concerned about memory. If memory is fundamental to intelligence, then how do we represent it within a symbolic framework that allows for logical inferences and the manipulation of abstract knowledge?
I think we need to focus on developing AI systems that can handle spatiotemporal information effectively. We need to develop algorithms that can translate between different coordinate representations and reason about change over time. I suspect that the translation between different coordinate systems, for example, pixel coordinates in an image, 3D world coordinates, is a fundamental barrier to true understanding. And the current deep learning approaches seem like brute force attempts to mimic intelligence without a clear understanding of the underlying principles of how memory works across different scales and in diverse spatiotemporal contexts.
Those are all excellent suggestions. It sounds like there's a lot of work to be done. This paper highlights a critical challenge in AI: how to build systems that can reason about cause and effect in a reliable and unbiased way. By drawing on insights from neuroscience, symbolic reasoning, and spatiotemporal analysis, we can hopefully develop more intelligent and trustworthy AI systems.
Yeah, it's a complex problem, but I'm optimistic that we can solve it. Deep learning has already made tremendous progress in recent years, and I think we're on the cusp of even bigger breakthroughs. Just need more compute and more data.
I remain skeptical that deep learning alone will get us there, but I'm hopeful that a more holistic approach, combining the strengths of different techniques, will ultimately lead to AGI.
I agree. It's going to require a multifaceted approach, combining insights from different disciplines. The challenge is to find the right balance between data-driven learning and symbolic reasoning, and to develop AI systems that can truly understand the world around them and time.
Well, that's all the time we have for today. Thanks for joining us on Cognitive Spirals. We hope you found this discussion informative and thought-provoking. Until next time, keep exploring.